Good afternoon, everyone. So this is definitely going to be more more dev than ops presentation because first of all, I don't have any slides, and this is going to be Java related. So does any of you program or know Java or something around it? Okay, great. So I'm going to be trying to do this as language agnostic as possible, and just to give you some basic thoughts how Hystrix works. So this is basically a Java library. You're using it in Java or in any other JVM language. And the idea behind it is that it tries to isolate errors from your application. So every time you're calling an unsafe code, let's call it this way, it will try to isolate it. So for example, apply timeouts, do fail-fast behavior, and so on and so forth. So that's about it. Let's just jump straight into a problem. As you can see, I barely have some code samples. I hope it's visible quite well to you. So this is a Java code. This is fairly simple. If you don't know Java, it basically just goes into the internet and fetches some resource, for example, some HTML, but this can as well be a SOAP or RESTful call. This can just as well be doing a query to a database, whatever. And this works. This is, by the way, a lousy test. I'm not using this code for testing. It's just like a useful way of running stuff. So this works. However, it might break under circumstances we haven't yet anticipated. So for example, imagine we don't have internet connection. This is simple. We just get an exception. Imagine we have a problem with DNS. We have a problem of router configuration, whatever. We all have failures, and we have to somehow anticipate them and program against them. But the worst thing that can happen actually with this code is that every time we were trying it, and on staging, on test environment, whatever, it always worked within like, let's say 100 milliseconds or maybe a second, and suddenly it takes 30 seconds, a minute, whatever. So we now have a system that used to work correctly, but suddenly it just stalls. It stops. It seems like it's hanging. It doesn't serve any requests, so on and so forth. So this is a major issue, and there's like a very simple solution to it. Do you know how to just like make sure our system doesn't get stuck? Yeah, restarting is a good idea, but let's just do it without any people interfering. So we can apply a timeout, and this is fairly simple. If you don't know Java, we're basically creating a thread pool here. And a thread pool, I'm going to explain it in like one sentence. A thread pool in Java is basically a bunch of threads, background threads that are created for you, in this case 10. And then there's a queue in front of this thread pool. So every time you're putting something in a thread pool, so you want to execute something in background, you're actually putting it into a queue, and then if there is an idle thread, a thread in a pool that doesn't do anything, it will just go into this queue and grab the first task. So this sort of works, and this is what you would see on most of the examples. This line is actually crucial. So this one tells us, okay, I placed some work in a thread pool. I can go on with doing some other stuff. For example, I can do another query, or I can do some CPU-intensive stuff, and then as I'm saying, okay, I want to wait at most 1 second for the result. And this works, so we have like a soft limit here. However, there are a couple of more issues with this code. For example, and again, this is in all examples you'll find in the internet. For example, the queue that is associated with this thread pool is unbounded, which means every time you're placing something, this queue just keeps growing and growing. Of course, if there are processing threads, so if there isn't any stall in the system, they will take items from this queue. However, if your backend system becomes slow, so you're having like a problem with a database, a problem with third-party API, let's say a Facebook or Twitter API, doesn't matter, this queue will just keep getting longer and longer and longer because all the threads are already occupied by doing a blocking network call. So you'll get an out-of-memory error and your application will crash, even though it's not really our application's problem. And it also misses a lot of other stuff. For example, I would like to have a lot of metrics here. I would like to know what is the average queue length over time. I would like to know what is the execution time distribution, so on and so forth. And there's one really important heuristic, which is actually the clue in Hystrix. It's called, this pattern is called fail fast, and it's implemented in the form of a circuit breaker. We will really go into details with a circuit breaker in a second. But for now, you should just understand that if we are running a piece of code, and for the last 5 seconds, 10 seconds, whatever, it just kept failing over and over and over again, then there's simply no point in running it again, because we can apply this heuristic that it will probably fail again, so there is just no point in running it again. However, implementing it correctly is really hard because we just have to keep track of all this stuff, like how many times this piece of code failed within like some rolling window, what was the rate, and so on and so forth. So as you can probably imagine, this is what Hystrix is about. Let's just go look at this example first, and let's just go into a Hystrix example, so how it looks in Hystrix. And this is relatively similar. You don't actually see the full picture here. So we replaced callable. If you don't know Java, then callable is basically a wrapper around some block of code. When we hadn't Lambda expressions, we just used like a callable, for example. So we replaced callable with something that is called a Hystrix command. So everything that is potentially unsafe, like typically going to a network or going to an I/O drive, whatever, everything that can potentially be unsafe, we are wrapping it in a Hystrix command, or to be precise, in this run method. And we have a bunch of configuration that's not really important. So let's see how it's being used. So we have a command, a new instance of this command. We just created it, and no further setup is required at this point. And then we simply say execute. Everything I described earlier is actually handled for you. So underneath, Hystrix create a thread pool for every type of command. So for every instance of basic download command, there's going to be a thread pool. It applies timeouts. So by default, this command here will not take more than a second. So this is like a hard timeout here. And also it applies this mechanism called Circuitbreaker. So if a command fails too many times within last few seconds, let's say, it will actually cut off this code entirely. So it will never again call run, or at least for a given period of time. It will not run this method again. Instead, it will just immediately throw an exception saying, okay, the circuit breaker is closed, so I'm not really, I'm off. I'm just letting it go. I'm not calling this code because it's broken, so just go fix it. Of course, it's like a very simplified explanation, but we'll see it in detail in just a second. Okay, I think it's about time to actually show you some demo. I think you saw enough. So here I have a really simplistic web application. It has an external service. So imagine this is a database, this is a third-party API, this is going to a network drive, whatever. I actually built in a throttling into this simulated backend service so that it cannot handle more than 10 concurrent requests. This will be important later. And I have two endpoints. One is called unsafe, so there will be a web application that will handle /unsafe requests, and it just calls this service directly. And another one called safe does the exact same thing, so it just delegates to unsafe. Let's just make it a little bit more readable. So it does exactly the same thing, calling the external service. However, this time it wraps the call in Hystrix. I think I removed this one. Okay. So we have two methods. One is protected by Hystrix, the one is not. And what we're going to see right now is how they behave in real. So I'm starting up the application. It should be up in right now. Oh, I'm actually going to run it in a different configuration for the moment. So we're going to start the application, and I'm going to use a tool called AB for Apache Bench. Do you know this tool? Have you heard about it? AB, Apache Bench? It's basically, I wanted to say JMeter for command line, but you might not know JMeter as well. It's like a load tool that you can use from the command line. It has like 2 valuable parameters, so that should be enough. Okay, I think the application should start up like now. Cool. It's running up. So let's just go to the terminal. And just to show you how this application looks like, and there were a few parameters that I haven't explained, so I will do it right now. Do you see the terminal? Make it a little bit bigger. I think it should be fine right now, or maybe even bigger, why not? So I'm just gonna go for Carl and call this service. I should have it somewhere here. Yeah. Okay, not AB right now, but Carl. So I'm running first I'm gonna go for unsafe. I'm running it, and it has a couple of useful parameters. We're gonna use these parameters to simulate the real life situations, like the backend server being slow, or the backend server throwing an exception. So these parameters, duration, standard deviation, and failure probability, are actually passed directly to this external service via query parameters. So we have all of them here. And basically the external service will like honor them, so it will become slow, or it will start throwing in exceptions. But rather than looking at the implementation, let's just make one simple request. So I'm running it right now. and the duration is 50 milliseconds, and failure probability is 0. So we should almost immediately get 200, okay? And here it is. So that's fine. Here's my little simulation tool. So let's run again with failure probability 1, and this time we're going to get 500. So that's about it. And the unsafe endpoint behaves the same way, at least for now. And of course, I can increase the latency. So, for example, 5 seconds, and then I'm going to get a failure. However, I have to wait for this failure for 5 seconds. So the tool I was asking you about was AB. And there's not really much to describe here. AB is basically a load tool, so I can say AB, number of requests 1000, and concurrency 5. So this will execute 1000 requests from within 5 concurrent clients. Let's go for 0 failures at the moment, and let's make it quicker. So not 5000 milliseconds, but just 100 milliseconds. I hope you can see it, yeah. Okay, so running right now. And it just runs the load test right now. I can interrupt it at any moment. I just want to run it till the end for the first time. It actually issues plenty of requests to my application. So if you look at the logs here, they are rather crazy. Oops. And the test is almost done. So what we're going to see in just a second, it will be a time distribution. So it will show us what was the distribution of responses within our application. And this is exactly what we expected. So we get 50% of the requests were faster than 97 milliseconds, and this is correct because that's what we asked here. Now it wraps, but it's 100. And I also added some standard deviation so that it's not that not that flat. So this is precisely what we expected. And one parameter which you can't see, but I will just scroll up, is the number of failures. So we have 0 failures, and this was to be expected because we specified now a failure probability of 1. It's not this request, it's this one. Failure probability of 0. So let's make it 0.7, which means 70% of the requests will fail after, on average, 100 milliseconds. Running the test right now, it will actually take a little bit, but what I'm expecting to see here is about 700 requests failed, and the response time will be more or less the same. So we're going to get around 100 on average. So we're almost there. I really don't want to interrupt it because it will be easier to calculate. And we're done. So the response times are more or less the same. I think it just transfers more data due to an error. However, if we go here, we have 680 failed requests, which is more or less what we expected. It's random. Okay, and just to run a couple of more experiments, what will happen if failure probability is 0? However, I increase the load, the duration. Okay, we already saw that. It was like damn slow. But let's just run it. So we're not going to wait for it because it will take ages. So I'm just going to interrupt it after first few requests if they come ever. Never mind. 50th percentile is 5 seconds, and most of them fit like in 5.5 seconds. So this is more or less what we expected. And one last thing I've mentioned. Remember I said that in this external service, this one, I actually added throttling, so it cannot handle more than 10 requests concurrently. And here I was spamming it with just 5 concurrent requests, so that was fine. So the backend service wasn't saturated. But what happens if I say 50 concurrent requests and the duration will be, let's say, I think I lasted, yeah, no. And the duration will be like 100 milliseconds. Can you, like, from the top of your head calculate what should be the average response time if I have 5 times more requests than the backend service can actually handle? And each request takes about 100 milliseconds in this backend service. Can you guess? Okay, let's just run it then. So the situation as we have right now is that we have a service that can handle up to 10 requests concurrently, but we have 5 times more clients. So for every single client, we have 4 clients that are actually waiting and sitting idle. That's why the average response time is now more than 500 milliseconds, even though the backend service can reply within 100 milliseconds, and this was to be expected. Okay, we went through all of this just to see how Hystrix can help us. So remember, we had 2 endpoints. One was called unsafe, the second one was called safe. They do exactly the same thing. However, in case of safe, we'll actually have all of this wrapped in Hystrix. So what will Hystrix do? So first of all, let us see what's going to happen if we have the exact same scenario. So 5 concurrent connections a safe endpoint and no failures. It should behave exactly the same way, so we will get the same response latencies, and basically there is little to no overhead introduced by Hystrix. So I'm running it right now. I'm gonna interrupt it because there's just no point in waiting for it. 50th percentile, 114 milliseconds, that's like what we expected. Now, what will happen if I increase the failure probability to 0.7? Remember what happened last time? 70% of the requests failing, remember? Yeah, so we expect to get more or less 70% of the requests failing as well. Let's just run it right now. And oh, it's faster. So something has happened, definitely. In previous case, I'm just gonna reply what was happening previously. Previously, when we were calling unsafe with 70% failure probability, it was like, 100 milliseconds on average. And here we have it. However, if we're calling safe version, which is this one, it suddenly goes much faster. And the average response time is like 6 milliseconds. So definitely the service responds faster. It's much faster. And this is the pattern. Do you remember what kind of pattern it is? I was actually describing it a couple of minutes ago. It's a circuit breaker. However, there's a trade-off, or actually a side effect of it. So for how many requests we had? No, never mind, we're gonna calculate later. So we had about 1,000 requests. Oh, it doesn't add up. Let's just run it again, it's safe, yeah. So for 1,000 requests, we should expect about 700 failed requests. So let's go through it again. Completed request. I have just one that's really, non-200 responses, 1,000. So basically almost all of the requests, it really depends on how I run the simulation, but much more than 70% of the requests, actually almost all of them, failed. And the reason for that is Hystrix opened, and this is like the official terminology, opened a circuit breaker, which means it cut off the problematic code entirely, and it was no longer executed at all. However, the side effect of it is that all requests, not only the 70%, but all requests, from our perspective, failed. But at least they failed fast. So now we have to think about it for a while. Is this a good idea that our application fails more often than it used to? However, it's actually faster. And this is actually based on some empirical study that a user, imagine you're sitting in front of a web browser. So let's start from this one. Imagine you're sitting in front of a web browser and it's just white. So you're typing in an address and it just doesn't work. So, and by doesn't work, I mean it's blank and it doesn't show anything. That's kind of frustrating and you have no idea what's going on, so you just keep refreshing and refreshing. But if you enter a website and it says immediately that there is maintenance and please come back later, it's actually a better idea, even if it happens a little bit more often. And the empirical study I just mentioned was that they were testing the behavior of users, and people are more likely to abandon your website if it's slow than if it's showing site under maintenance. So site under maintenance is actually a better message sent to a user because it knows that something's going on at least, than just keeping it like very slow and not doing anything. So that's the basic idea of Hystrix. So it makes sure that we don't sit and wait for things that are already broken, and it also applies timeouts. So here we have another time. Let's just run another example. Here we have a safe endpoint. 100 milliseconds. This should just work. There is no like. We already saw this a couple of times. But what happens if we increase the duration up to, let's say, 2 seconds? And I think I mentioned it, a command in Hystrix by default has a 1 second timeout, which means it will wait at most 1 second for the command. And if the command didn't finish within this second, of course it's configurable. If the command didn't finish within this second, it will just like cut it off and say, okay, it failed. Because from our perspective, it doesn't really matter whether the system, the underlying system, the backend system is failing or is slow. It's just like, it's just so it happens. So if it's slow, we are just assuming it's failing. Okay, so let's just run it again. This time with 2 seconds, and it should be damn slow. I'm running the safe one, and suddenly it's faster. You see? So this is again what Circuitbreaker did. We weren't waiting for the backend system for 2 seconds every single time because maybe it was failing after these 2 seconds. So there's just no point. If you haven't met the SLA, just let it go. I'm not really touching you anymore. I'm just opening the circuit breaker and I'm throwing the fail fast immediately. Is this clear so far? Okay, cool. So let's go back to the code because there are quite a few features that I want to explain. So this is the circuit breaker in details. I'm just going to try to scroll it the way so that you see it. And now we're going to explain how the circuit breaker actually works in greater detail. So we have a command, and by the way, all these options that you're going to see are actually defaults, however, I'm showing them for reference. So we have a command, and it has a circuit breaker enabled. Circuit breaker is this fail-fast mechanism that just cuts off my command. So in default configuration, let's start from here. In default configuration, I am keeping 10 seconds of statistics. So there's like a moving window of statistics, and I'm keeping the most recent 10 seconds of statistics. Within these 10 seconds, every command, by the way, circuit breaker, and this is important, circuit breaker is per every command. So there's no global circuit breaker in your application. Every single command type has a separate one, just like a separate thread pool. So if within these 10 seconds, more than 50% of the requests are failing, so more than 50% of the commands are either throwing an exception or timing out, this is another configuration parameter, and there are more than 20 requests within this window, so more than 20 requests and more than 50% error rate, please close the circuit breaker. Please open the circuit breaker. And when the circuit breaker is open, we are not really letting go our code in the command, but we're just failing out immediately. We're just failing immediately. Now, of course, this is not permanent, so we don't have to restart the application to wait, or we don't have to restart the application to close the circuit breaker again. A naive implementation would just, after 5 seconds, and this is not how it works, a naive implementation would just, after 5 seconds, close the circuit breaker, and that's it. However, if the backend service has an issue, and the issue might mean it does a garbage collection, maybe it's restarted, maybe there is a network problem, whatever. If the backend service has an issue, it's very likely that it's not gonna fix itself within 5 seconds. So what Hystrix does, and this is actually really clever, it goes into a so-called half-open state. And in the half-open state, it issues exactly after 5 seconds. After 5 seconds, it goes into its state, and it issues exactly one request. So exactly one request will actually touch the backend service, or it will actually go to a network call, whatever. However, all the other requests are still failing fast. So after 5 seconds, one request, like a probe or like a sample, is being executed. If it succeeds, the circuit breaker is closed again. So it means that the system healed itself and it recovered. If the single sample probe failed, well, we go back to an open state and we wait another 5 seconds. That's how it works. Is that clear? There's actually be a demo, so you will see how it works in practice. Okay, so this was a circuit breaker. There are a couple of parameters that I'm not going to explain to you. For example, you can configure a thread pool size, a queue size, and so on. This is not really that important. So what I want to show you, and I understand this is a DevOps conference, so there will be a little bit about metrics. So every Hystrix application can optionally stream statistics in JSON format. So I'll actually go to a terminal. And by default, this is obviously configurable. Every Hystrix application has an endpoint or an address called hystrix.stream. And if I go to it, I hope this will be visible. If I go to it, I'm going to get a lot of JSON data that's going to be pushed into the client immediately. So let's just do it again. I think I can just decrease the font size so you will actually see that something's going on here. So it tries to push a lot of data into the client, and this data contains a lot of useful information. For example, what is the status of every single Hystrix command? Let's just go through it a little bit. Okay, so here we have a Hystrix command called save, and this name was assigned to a command when we were creating it, and you have information like how many requests within the last 10 seconds, how many failures, what were the response latencies. It's all empty because nothing happens in the system. So I can actually run a demo and you will see some data. So this stream, which is being produced in real time all the time by Hystrix, is actually very useful. It has information about every command and every thread pool in your system. So you can build some sort of monitorings or dashboard or alerting system if something goes bad in your application. Luckily, there's already a tool like that. It's called Hystrix Dashboard, and it's part of the official release, so I'm going to run it quickly. This is basically a JavaScript application that you can run easily and deploy somewhere. It will take a little bit of time to execute, so I'm going to explain how it works. So what this application does is that it connects to a given stream, parses this JSON data, and shows you what's happening in your application. Oh damn, this is really slow. So I will run some benchmark in the meantime. I think this one is fine. And this one should be up in just a second. Oh yeah, so you don't see it, but it says it's open on localhost 7979. Almost there. Okay, so this is the application. It's terribly simple. It asks me to enter a stream URL. What should I put here? Come on, people. So it's the application address plus hystrix.stream. So it's the same JSON that we used to see in curl. So I'm running it right now, and more or less it won't display anything because nothing's going on with our application. So let's run some benchmark. Okay, so here I have a benchmark that's being executing that will execute the safe endpoint with some data. The command is still empty. Not sure why it's not processing anything. We'll just refresh. Come on. Localhost 8080. I think the address is correct. I'm just going to check it. Nope. Localhost. Okay. Localhost. Okay, so now it should work. You won't get the wow effect. Okay, so this is the dashboard. It's painted in JavaScript and it's using vector graphics, so I can safely zoom it. So there's a couple of information here. For example, it says how many times an action was executed within last 10 seconds. And we have an information about the total cluster. More on that in a second. We have latencies, error rate, and so on and so forth. This is an important thing. It tells us whether the circuit breaker is open or closed. Closed means that the system is operating normally. Okay, if I stop the simulation right here, immediately in real time I see that the system is not doing anything. So this is truly a real-time monitoring dashboard, and it's really useful. I think if you're gonna stare at it for a couple of minutes, you're gonna realize what all these bubbles and charts mean. Okay, so now let's run a different simulation, this time with lots of errors, or maybe just 20%. So if I have a 20% error rate, it immediately shows us that a few commands within this time window were failing. However, the circuit breaker is still closed because 20% is less than 50, which means we haven't reached this threshold of 50% failures that will actually close the circuit. Okay, so it works. We have an information how many commands failed and so on and so forth. If our backend system is becoming really slow, we would also get rejects, which means we have no processing power and we are just rejecting this command because there are no more threads in a pool. Of course, all we want, I believe all we want to see now is how the circuit closes. So let's go for 70% as we were looking at. So now it's empty, nothing happens, and I'm gonna run the test now, and something is happening, and you will see circuit breaker flickering, and now it's open permanently. So the request volume instantaneously increased into like 800, 900 requests per second, and this is what they call fail fast. So we really immediately get a response from the system. It's failing because of the circuit breaker. However, it's immediately being returned. And you see that sometimes the circuit tries to close itself because this sample request actually succeeded. It had 30% chances. But all in all, we have a system in a really unstable condition. And even if you don't understand all the numbers and whatnot, if you look at this dashboard and it looks like this, with this gigantic red ball, I think you can safely assume that something bad is happening on production. I mean, even if I take off my glasses, I can actually see that something bad is going on. So this is how a circuit breaker works in practice. I can stop the demo right now and just go for something smaller, and immediately the dashboard would actually become green, and the response times are much bigger. So this is how circuit breaker works. I think this is understandable, more or less. Okay, cool. So we have a dashboard. We see how it works. There's a tool called Turbine. I will again show you how the dashboard looks on the main page. So this is the dashboard, and here we are basically pasting. Can I go for, yeah. So here we are pasting the stream, the address of the stream. However, it's impractical if you have the same service, microservice, whatever, deployed multiple times or scaled horizontally. Then you will have multiple Hystrix streams, so multiple sources of statistics. It would be really nice to aggregate it so that you just have one huge stream showing you the overall health of the system. So let's say total number of requests handled by all your instances, or the average response time on all instances. And this is what Turbine is about. I don't really have time for running a demo, so for the moment I will just quickly describe that Turbine is basically a server that sits between your applications and this dashboard. It connects automatically to all your instances, and there's a pluggable discovery mechanism, so you can use hard-coded addresses, console, Zookeeper, whatever. And then it produces a single stream with all this data aggregated together. And this single stream also has an address, and this is what you paste in here. If you look closely, it actually has a Turbine example. So there's like /turbine stream. You have to look very closely. So this is what Turbine is, and it means this dashboard is also useful if you have large clusters. And by large, I actually have, I don't have a demo, but I do have a screenshot, because I don't have slides as well. So this is a dashboard from Netflix. It shows their system. I mean, it's quite impressive if you think that they're handling more than 3 million requests per second within a cluster for a command called video metadata something. And you can see that they have a cluster of 565 nodes. So they have Turbine instance that connects to more than 5,000 microservices, gathers all this information, and displays it on a single chart. Very useful. Okay. Every time I'm introducing the dashboard to someone, they're actually asking, why is it so short term? Because if you look at it, let me just go back to it. So if you look at the dashboard, oh, it still keeps running because I have a simulation, so I don't want to melt my computer. Let's stop it. Okay, now it should go to 0 in a few seconds. So it actually shows statistics for just last 10 seconds, and this is useful if you are looking at your system in real time. However, it becomes a problem if something was going on last night or maybe last Friday, whatever. And Hystrix, by design, doesn't store these statistics anywhere. It's only in memory. And they are claiming that it's just impossible to keep all of this data in a storage and still be real time, which is not really true. I'm not going to show you the full setup, but you just have to believe me that it's a matter of adding a bunch of dependencies into your application, a bunch of jars. And you can actually set up a bridge between Hystrix and Graphite. So all this data that you see on this chart can be automatically pushed into Graphite. Do you want to see a demo of it or how it's set up? Okay. So I'm actually going to go for demo because it's more interesting. I have a Docker image here somewhere, I believe. Yeah. So I have a Docker image that starts Graphite, Grafana, Carbon, Elasticsearch, and whatnot, and some dashboards. So it should be running right now under this address. I have problems with typing today. So here's a dashboard, and it's empty right now, so we're going to see how it looks in just a second. And my application is configured, or it can be configured the way that it will publish these statistics into Graphite directly. So I'm just going to have to start it with a special parameter that will connect to Graphite. It will start in a bunch of seconds. Now we have Grafana running. Now I'm going to run this load test, which is here. The parameters look okay. So let's just, okay, so now I have a benchmark running just to see it. I think it should refresh quite soon. Yeah, so we have a dashboard with real-time short-term statistics. However, if I go to Graphite, and this is not a built-in feature, but it turned out to be really simple to set up. If I go to Graphite, I think I have it on some dashboard. Let me look. I was just setting it up a few seconds ago. Yeah, here it is. So changing it from an hour to 15 minutes, maybe. Or maybe I have some history. Yeah. So this is what I was running during the previous presentation. So we have so we have data from like last hour, I believe. You can actually zoom it in. And these metrics are latency. So we have 50th, 90th, and 99th percentile latency. Actually, if you look at this dashboard, every single number you see here is automatically published to Graphite. Moreover, there are more numbers that aren't displayed on the dashboard because there's simply no space for it. And you can still see them here. Okay, it was supposed to be a real time as well. So let's go for 15 minutes. And this is actually our simulation refreshed every 5 seconds. And just to prove it, I can change the number. What should it be, the duration, instead of 100? I want to prove that it works. 10. So if I go for 10, then all these numbers should go down in just a couple of seconds. So the simulation started. We should see it right here. Okay, so we have a much smaller response times here. I'm intentionally going to this dashboard so that Graphite updates itself. This data should be much faster, and we have much more requests per second being handled. And if we go to Graphite, do you see it? We actually see a drop here, which means it was reflected in Graphite. So we have best of both worlds. We have real-time statistics in this built-in dashboard. However, by adding just a bunch of dependencies, if you're really curious, I can show them to you. Just by adding a couple of dependencies into your Java application, you will immediately see, you will also get data in Graphite, which I think is really useful. I believe we are more or less running out of time. Let me just check whether I have something more something interesting for you to show. Not really. Oh, yeah, there is. There is a feature called request batching. I have an example of it, but we just don't have more time. So the idea is that sometimes, and I'll just go for an interface, sometimes you have an API that you can call two ways, either for a single piece of information or for multiple pieces, like multiple IDs. So rather than fetching one person from a database, you can fetch a whole page, or you can fetch a collection of people. So Hystrix is actually capable, but this requires a little bit of code, but not a rather trivial one. Hystrix can actually collapse multiple concurrent requests for similar pieces of data. So let's say, for example, one request asks for a person with ID 1, and a second request asks for a person with ID 2. And Hystrix can actually collapse these two requests and issue just one. And this obviously has an impact on bandwidth, because or not really bandwidth, but latency, because we have less round trips to a database or to an external server. Of course, there is a downside as well, because Hystrix, in order to perform these collapsing, has to actually wait for the upcoming requests. So when a first request comes in, Hystrix starts a timer that takes, let's say, 10 milliseconds or 100 milliseconds. And within this time window, it will start collapsing or batching all the other requests that come in. And only after 100 milliseconds or 10 milliseconds, of course, it's configurable, only after this configurable time window, it will issue one single batch request. So we are introducing latency into our system. However, if it's a really high volume one, if it's a system that handles a lot of requests concurrently, this can significantly reduce the load on the backend services. I think it's about time, so do we have time for a few questions? Okay, I just heard that we have time for 2 questions. So. Okay, so thank you very much. It was a pleasure, and have a great lunch.